All right. So, hello everyone. My name is Reza, and I'm an assistant professor. Welcome to the civil seminar. Today, we are very pleased to have Dr. Amir Ali Khan, who is the manager of the Water Rights Investigations and Modeling section with the Newfoundland and Labrador's Department of Environment, Climate Change, and Municipalities. So Dr. Khan's responsibilities there include water rights, flood risk mapping, flood forecasting, flood alerts, as well as climate change adaptation. He has developed the climate change flood risk mapping template that is currently used in Newfoundland and Labrador. So he has received his PhD in civil engineering from the Memorial University, and he is currently also a sessional instructor there as well. Their work has been quite well received, and they have received awards, including the 2005 Government of Newfoundland and Labrador Individual Public Service Award for Excellence for Innovation and Service Delivery Excellence, as well as another award by Esri Canada for drinking water quality GIS application, and others. So they're doing great work in everything related to water, including flood, focus of flood mapping and flood alerts. Dr. Khan has also been working on several international technology innovation and water resources projects, including the European Space Agency, as well as the North American Treaty Organization. And today he's going to walk us through the Newfoundland and Labrador Climate Change Floodplain Mapping. And with that, the stage is yours. So thank you very much.
Reza, thank you very much for this opportunity. Hello, everyone. So I'm going to be, as Reza said, I'll be presenting on the Newfoundland Labrador Climate Change Floodplain Mapping Program. This presentation typically takes 2 to 3 hours. So I'm going to just try and take you through some highlights here. And then we can follow up with questions, or you can follow up afterwards, and we can go in more detail. If you're interested in different aspects, you can email me or email Reza. He can forward it on to me, and I can try and respond to your queries. Okay. So so I work with the Water Resources Management Division. Just a quick overview. It consists of 4 different sections, and I'm the manager of the first one here, the Water Rights Investigations and Modeling section. We are very lucky in Newfoundland that everything to do with water is in one division. So it makes it very easy for us to coordinate between the different sections, and we can do a lot more work with less people. It also helps that we have a very, very good Water Resources Act, which looks at everything from water rights to protection to groundwater, and it's all in one act. So it really makes our work so much easier. So I'm going to be talking specifically today about floodplain mapping. And in Newfoundland, floodplain mapping meant identifying a community which had repeated flooding incidents and going in and mapping out the 20-year flood zone, which is shown in orange, and the 100-year flood zone shown in yellow. And this format essentially came from a federal provincial program called the Flood Damage Reduction Program. And it was through this program that throughout Canada in the 80s and 90s, most of the flood risk mapping was originally done. And that's why when you go across Canada, you'll find a lot of the maps are very similar. The colors are similar. The terminology is similar, because that was the intention of this federal provincial program, that is to identify, trying to create a common template across Canada for flood risk mapping. And a lot of studies were done. In Newfoundland, we did around 37, 38 areas were mapped under this program in the 80s and 90s. But this program came to end in 1996. And after that, we didn't do any flood risk mapping, though the floods continued. In fact, they got more and more frequent, but we didn't do any mapping until 2008. So we have a town on the west coast of Newfoundland, which is called Stephenville. And this was the site of a former American military base. And as you know how military engineers are, they come in and they like to have everything laid out at right angles. And they did that to this town. And there was a river, poor river, which was meandering through their base. They straightened up the river. So what happens now, every 10 years or so, there's a major flood in that river and the river changes course. It's trying to find its old course there. So there was a major flood in 2005 there, because of which we got funding in 2008 to redo the flood risk mapping there. The previous study had been done in 1996, and almost on dot, within 10 years, we had the major flood there. So when I started preparing for this study, I started looking at the IDF curves. I was just trying to get the data ready so I could give it to the consultants. And I started comparing the 1990 IDF curve. And luckily, we had a 2007 IDF curve for the site. And I realized that if I looked at the 24-hour 100-year precipitation, it had gone up by 13% in 17 years. And if I looked at the 12-hour 100-year precipitation, it had gone up by 19% in 17 years. Now, this can happen at a site where the station is new and it's gathering new data. But in 1993, there was already 23 years of data there. And in 2007, there was already 39 years of data. So that's a big change for these years. So it made me think, okay, is this climate change? Is something happening to the precipitation? And if it is, how do we capture that in the flood risk mapping? If you understand, flood risk mapping is based on this whole paradigm that we look at the past rainfall record or flow record, and based on that, we define what would be the 20-year flood zone or the 100-year flood zone. Some places do a 500-year flood zone, some places do a 200-year flood zone. But the whole idea is, let's look at the past precipitation or stream flow data, do a statistical analysis on that, and define what is the probability return periods for these storms. So we started saying, no, wait a minute, let's also see if we can look into the future, like get a glimpse into the future. Lucky for us at that time, Environment Canada had a regional climate change office in Dartmouth. And at that time, there was a person there, Gary Lyons. He just was doing some experimentation. And so remember, this is 2008, okay? This is not now when you've got all these ensembles and you have all these ready-made data sets there. So at that time, he downloaded two models, the Hadley model and the CGCM2 model. And for Stephenville, he looked at two sets of predictions. If we took his worst case scenario, what we found that there was, by 2050, the precipitation was supposed to change from where we were by 35%. So, and actually what we were seeing, this 13 to 19% precipitation change was on track. And when we put that precipitation into the hydrologic model, it said that the flow was going to increase by 55%. And this got me thinking that, okay, if we're going to do this flood risk mapping study, we'll do the normal flood risk zones that we do based on past data, but let's try and see what happens if this trend goes into the future. How is that going to impact the flood zones? Now, you think this is easier, it's easy to do, but at that time, nobody was doing this. And in fact, when we proposed this, there was a lot of opposition from a lot of my engineering colleagues, because this is not how flood risk mapping was done, right? It's something different. Well, so what we did is, when we had the study done, we asked the consultant to rerun the hydrologic model and the hydraulic model with the climate change precipitation IDF that we had, and see what is the impact on the flood zone. Even the consultant was reluctant to do that. So we finally said, okay, let's put that in the sensitivity analysis section of the report. And when they did that, this is what we came up with. So it's really interesting. The yellow zone is the normal 100-year flood zone. So this is the normal 100-year flood zone that we would get in the study. The green area is the 100-year climate change flood zone, that the flood zone that we would get by incorporating the revised predictions that we're getting for rainfall. And we, for the first time, could see what the potential impact of climate change would be on flood zones. So when we looked at it, and it's interesting, it's not that everywhere the flooding got worse. So if I look in these areas here, for example, can you see my mouse? Okay, so if I look at the areas next to Knowles Pond, okay, you can see the mouse, perfect. You'll see that both the flood zones are overlapping on each other. So there's really nothing happening here due to climate change. But if I look at the downtown part of Stephenville, you can see that the 100-year climate change flood zone is far more extensive than the 100-year regular plain. And this told us that there's a potential that in the future, this area could be subjected to flooding. This was new. For the first time, we were seeing this on a map. And we ran this by the town manager, and we were interested to see what his reaction would be. And he looked at it and he said, wow, this is amazing. He actually liked it. And because he liked it, it stayed in the report. And going forward from there, we decided that every flood risk mapping study that we do will include climate change. So we were the first province in Canada to do this at that time. This is the first provincial study to look at this. And that year, if you look at our study, which is on our webpage, I'll show you, you'll find this in the sensitivity analysis section. It's not in the separate climate change section. But going forward, we have a clear-cut climate change section in all our reports, which shows these kind of maps. So this is really, really interesting for us. We brought this to the attention of some of our colleagues in Natural Resources Canada. They gave us funding to do 3 more studies to try and explore the concept. And in doing that, we decided that it was not enough for us to just map it, but we'll actually include the climate change zone in our provincial policy for floodplain management. So in Newfoundland, if you're building something in an area where the 20-year flood zone or the 100-year flood zone has been mapped, you have to get a permit from the province first before you can go ahead with that development. And if you're in the 20-year flood zone, we do not allow anything. The only things we allow there are marine structures, which are supposed to be there. Within the 100-year flood zone, we allow certain developments. We allow residential developments as long as the ground elevation is above the 100-year flood elevation. And we don't allow things like senior homes or hospitals, anything where it'll be an issue to evacuate in a major flood. So essentially what we did is we created a new climate change flood zone, which had the same conditions as a 100-year flood zone, which essentially meant is that what we said is that in Newfoundland, the 20-year flood zone will be defined by the traditional boundary, but the 100-year flood zone actually extends all the way to the 100-year climate change flood zone. I know there are no guarantees will flood there, but it is a high likelihood that area will flood. So based on that, we started applying floodplain management going all the way up to the 100-year climate change flood zone. And this, to my understanding, again, is the first such policy in Canada. It might still be the only such policy in Canada that regulates floodplain management in the 100-year climate change zone. Following that, we were lucky. We got money from the federal government. We got money from our own government to do a number of flood risk mapping studies. And as we did these studies, we kept adding to the template. As we learned, we added new things. And that presentation is a very long one, but I'm just going to touch on a few of those key things that we added. So first thing we did is we added sea level rise. So far when we said climate change flood risk mapping, it meant that we were looking at climate change precipitation. Lucky for us, our Geological Survey of Newfoundland in 2010 published a paper in which they gave predictions of what the expected sea level rise was for different regions for Newfoundland and Labrador. So there were 4 regions, and you could see the sea level rise was, greater than 100 here and goes less as you go towards Labrador, because Labrador is still rebounding from the glaciers we had. So sea level rise is not that high there, but it's higher in the island part. And so going forward, every study then now had the regular 20-year flood zone, the regular 100-year flood zone, but it also had a climate change 20-year and 100-year flood zone, which incorporated the future sea level rise in that. And the way you do that is when you run your HEC-RAS model, you incorporate the new sea level as the downstream boundary condition. So this was another thing we did. So going forward, all of our studies now include climate change from both the precipitation point of view and from the sea level rise point of view. One thing we realized is that every time we did a study, we would get these climate change predictions, and we realized different consultants were doing their downscaling differently. So what we did is, as a province, we went back to our climate change office, and we went out to our university. We had Dr. Joel Finnis there, the meteorologist in the Department of Geography here at Memorial University. And he looked at all of the models, and he selected an ensemble, and he came up with a climate change atlas for the province of Newfoundland and Labrador in 2013. In this atlas, we have predictions for precipitation, for dry spells, for heating days, as many variables as possible. We have a set of predictions, and this ensures that everyone in Newfoundland who's doing any climate change work is working off the same set of predictions. These predictions were updated in 2015, and there's been a new version that came out in 2018. So the major updates every 5 years. When the new IPCC results come out, the models come out, Dr. Joel Finnis goes back, reviews them, and selects an ensemble. And based on the ensemble, he comes with these climate change predictions including climate change IDFs. So for example, the current report is based on 12 climate models, 6 of them dynamic downscaling, 6 of them statistical downscaling. And based on that, he predicts the new IDFs base. He gives us the median value, the 10th percentile, and the 90th percentile value. And we go with RCP 8.5. We assume it'll be business as usual. So we go for that scenario there. So that's another thing we did. We standardized our climate change predictions. We've also included future land use. So in municipalities where they have land use planning and they know which areas they're going to develop in the next 20, 30 years, we assume those areas are developed in our climate change maps. So we also incorporate the impact of future land use. One thing we realized while working with consultants is that when you're dealing with hydrologic and hydraulic modeling, consultants like to keep tweaking the watersheds, the sub-watersheds. It's a bit of an art. There's science in there, but there's also a bit of an art in there. We didn't like that because what that meant is that when we were comparing a 100-year flood zone to a 100-year climate change flood zone, we were not comparing apples to apples because the modeler might have tweaked the watersheds a bit, might have tweaked some of the variables a bit between the two scenarios. So what we did is we implemented a digital workflow. We worked with ISRI Canada to create what's called map to map. And this is basically a workflow within the GIS software, which ensures that once a consultant creates the HEC-HMS model and the HEC-RAS model, we lock them down. Now, the only input changes that take place are in the precipitation inputs. Every other variable stays the same. We also did another thing. We standardized on HEC-HMS and HEC-RAS because we wanted open source, non-proprietary models. We wanted models on which there was a lot of publication, there was a lot of literature in the public domain. We did that. We also ensured that when they use HEC-HMS, they use the GeoHEC-HMS to pre-process the data, and they use the GeoRAS option to pre-process the RAS data. So the idea was to remove as much variability as possible, standardize things as much as possible. We made changes to our mapping. When we did the mappings in the 80s and 90s, we used what's called community mapping, and this is what it looked like. People now are used to Google Earth. So what we started doing is with every study that we did, we would acquire either remote sensing imagery or we would acquire aerial photography, and this is what our new maps look like. So you can actually see the homes, you can see a lot more detail. And we've done away with these kind of maps because people now relate more to the maps that you see on the right-hand side here. We also realized, so far we were using the DMs that came from the National Topographic Mapping Series. But when we did a study in a flat area in Newfoundland, we realized that those DMs, so this area we had LiDAR for it. When we compared the LiDAR to the DM from the National Mapping Series, we found it was off by 20, 30 meters in some places, which actually made the whole flood risk mapping useless. So going forward, what we decided was that what we will do is for every study, we will first acquire LiDAR for the floodplain. And the idea is then this way, the mapping that we do is accurate. Also, because we were acquiring LiDAR, now we started doing flood inundation maps. So we show you the depth of flooding. And this is really interesting because one, it's useful for understanding which areas, how bad the flooding is going to be. It also let us understand that in which areas could we actually flood-proof homes and which areas it was hopeless to do so. So if you're going to be under 2 meters of water, really most flood-proofing options are not going to work. But if you're within half a meter of water or 1 meter of water, there's a choice of flood-proofing options that you can use, right? So we actually have made this a standard product. And this is also made a standard product because our emergency responders wanted to know when they're responding to a flooding incident, how deep the water is going to be in certain places, right? And because based on that, they had to decide, can we put firemen in there or not? Can we drive a truck into that or can we not do so? So this is now another standard product that's part of floodplain mapping. We also, to help first responders, started to velocity mapping, which shows you how fast the water is. We also did this so that we could look at erosion potentials. So depending on what your kind of soil you have, in certain places, these high flood flows will erode your banks. So this gave us an idea looking forward which areas have high erosion potential. So the town municipality could use that as part of their shoreline protection programs. Then we combine the depth mapping with the velocity profile using this hazard matrix. And now we create this product, which actually tells you if it's a green area, you have to use caution there. If it's yellow, it's moderate hazard. It's danger for some like children and elderly and infirm. If it's orange, it's dangerous for most of the public. And if it's red, it's dangerous for everyone, including first responders. So now this kind of mapping has been made available. It's done as part of each study. And when it's done, it goes to the municipality and goes to our emergency measures organization. So if there is a flood, when they get to the spot, they actually, don't waste time trying to gauge the hazard. They have a good representation of the hazard already there. One thing we did, which was very, very interesting, is that as a part of flood risk mapping, we told the consultant to assess all of the hydraulic infrastructure. So every culvert, every bridge, we wanted the consultant to take pictures of the upstream end, the downstream end, do up a sheet on what the condition is. And we also wanted them to assess each structure for the current flows, the 2020 flows, the 2050 flows, the 2080 flows, and see if the structure had adequate capacity to pass existing flows and future flows. And this turned out to be really useful because the ones where it didn't have adequate capacity, we would flag in red, and that became a very useful tool for engineers and consultants and the towns to prioritize their infrastructure replacement, right? So if something didn't have adequate capacity for current flows, that was the highest priority. If something had adequate capacity for current flows, but did not have adequate capacity for, say, the 2050 flows, that went next on the priority list. And the amazing part is, because we could identify which culverts did not have what adequate capacity and what the capacity should be for climate change flows, what we're finding is that whenever municipalities submit applications for new infrastructure, they're designing it for the climate change flows. We don't have a policy requiring them to do that, but that's what's happening. There's one or two cases where it doesn't happen because the lay of the land doesn't allow a structure of that size to go in there. But in most cases, municipalities themselves and engineers themselves, when they're putting in new infrastructure, they're designing it for the climate change flow. So in a sense, this mapping is helping with climate change adaptation too. Since 2009, we have finished 9 studies. There are 2 which are currently in progress and should be finished by March of next year. And in all of these studies, we have implemented the things I've talked about. So the first one was Stephenville. And then going forward, we've started from 2012 onwards, we have sea level rise, inundation mapping, flood hazard mapping. And so we've made other changes in there to improve the standard. Consultants tell us that our flood risk mapping requests for proposals are among the hardest in the country to meet. All of our flood risk mapping studies are publicly available. So we have a web page. You can go to the web page there. It says flood risk mapping studies. You go there, every study is there. For example, this is the Waterford River area flood risk mapping study. We'll have the main report. If there's any updates, they would be there. The mapping would be there in ISRI format, in AutoCAD format. We also are now putting out the HEC-HMS models, HEC-RAS models. If the model is updated, HEC-RAS, that's also put out. And then we have all these maps I talked about. Remember these all, the velocity profile map, the climate change map. So we have all of these maps now which are being put out there too. And it's all publicly available. You can download. The files are quite big, 54, and some of them are 200 megabytes, but they're all publicly available. Not only that, on the same web page, we have a GIS application. So you can actually go in, zoom in any area. You can see the maps. You can print the maps. It's far more user-friendly. And the reason why we do this, my whole section has 5 people, out of which only 2 people are working on flood risk mapping. We want to make everything available to the public, so we are not responding to data requests, right? We're focusing on the work, not on the data requests. So that's our flood plain mapping overview. Are there any questions here before I move to how we're using this in flood forecasting? Or is that you want to hold the questions for the end? To the end? Okay, you're muted, Reza. Okay. So
sorry, yeah, we'll leave it for the end of the.
Okay, perfect. Yeah. So the program is the floodplain mapping program, but we're also using the results from this for flood forecasting, right? And let me show you a few examples. So we did a study called the Flood Risk and Vulnerability Analysis Project in Newfoundland, and we compiled a flood events inventory which goes from 1950 to 2014. Actually, we have now updated this to 1900 to 2014. So, but when we looked at from 1950 to 2014, we had 681 flood events, which were the result of 296 storm events. We plotted them by years, right? We also try and break down the events to try and see what was the primary cause of the events. We did analysis over the seasons, and we looked at the regions. We've got the east, the central, the west, and Labrador. And when we looked by the regions, we realized, and by season, we realized that all regions were more susceptible to flooding in winter and the fall, right? Which made sense to us. But we found when we looked at the cost of floods, the fall floods were the most costly. And the reason was the fall floods were due to post-tropical storms. So hurricane systems, which by the time they reached Newfoundland were post-tropical storms, or in 1 or 2 cases, hurricanes. So these were widespread. And so the damage was widespread from these. So we figured out we need to do something to sort of help these communities out. And because of that, we created what's called the Hurricane Season Flood Alert System, which we believe we're told by Wood that this is the first of its kind in the country. So what happens is from June 1st to December 31st, every weather system that approaches the province is tracked by Wood. So they have a really advanced meteorological center here. They track every weather system. And for every community that we have flood risk mapping, we have identified the 12-hour and the 24-hour, 20-year, and 100-year precipitation triggers. So these are the precipitation that would cause flooding, and they track for all of these 45 areas, and they look at what the precipitation is. And if, for example, if a certain tropical system is going to cause rainfall that's more than the 20-year or 100-year, it gets all flagged in this report, which is generated every morning. We get this report every morning. We pair this up with another report that tells you what the water levels are in our streams across the province. And we send this out to our emergency measures organization, which then contacts the towns and tells them that based on the forecast, and this is for the next 72 hours. So we do this every day, track for the next 72 hours. We tell them that there's a chance that you might have a flooding due to precipitation. And we ask them to go out and lower water levels where they can. We ask them to clean out culverts, inform residents. So we have this system here. The system also comes up with, there's a graphical form which shows each community and highlights it, whether it's going to be exceeding the 24-hour, 20-year limit, 100-year limit, or the 12-hour, 20-year limit, 100-year limit. And we pair this with another report, which is one you see on the left here, where we're looking at all our stream flows every day, 4 times a day. We compute if the current water level, current flow, what is the percentile value. So for example, if you have an alert for Corner Brook and you see Corner Brook is black, that means the flows are already in the high. That means they have less room for storage in the water system, then the chances of flooding go up high. If you have a flooding, precipitation alert here, but your values are, let's say, green, or which means you're in the 25th to 74th percentile, that means your risk of flooding is less. It's not a perfect system, but it's been very, very successful. Every year, this generates around 9,630 flood forecasts for these communities every year. And we issue varying from 40 to 80 actual flood alerts every year. So it's been very, very successful. So this piggybacks on our flood risk mapping program. Again, these are publicly available. We have a web page there. You can go and look at today's hurricane season flood alert. You can look at the current stream flow conditions. So there's this graphic, you can look it up there. We also have the whole season forecast. We have postseason reports, right? And we have details on the flood alert system there. What we also are doing is, because remember I told you we moved to a whole digital flow. One thing I didn't tell you is that we told consultants you can't just use statistical analysis to come up with return periods for flows. You can use that, but you also need to implement a HEC-HMS and HEC-RAS model for every flood risk mapping study, right? So what we're doing is we're repurposing those HEC-HMS and HEC-RAS models. We're putting them together to come up with real-time flood forecasting systems. And we're implementing this on 3 watersheds. One is the Churchill River watershed in Labrador. Then there's the Humber River watershed on the island, and the Exploits River watershed. The Churchill one has already been done. It's in operation. The Exploits and Humber ones are in progress. They're being developed right now. So what we have here for the Churchill one, this is our largest watershed, 94,000 square kilometers. It's regulated by a dam, but between and we're building a new dam in there, which is already ready. Between the new dam and the ocean, we have an ice cover that forms, and there is ice jamming that happens quite frequently there. So what we have done is we've created a system that runs all the time. So it automatically takes numerical weather predictions from Environment Canada. It puts them into HEC-HMS model. It runs them to the HEC-RAS model. And during ice conditions, it runs them to river ice. And it runs every day automatically. In the summer, it runs HEC-HMS and HEC-RAS, and it tells us what the water levels are going to be for the next 72 hours. As we enter fall and we see the water temperatures starting falling, it switches up into freeze-up mode. And what happens is HEC-RAS gets replaced by riv ice, which again is another open source river ice hydraulic model. It starts freezing up. Then during winter, it continues using the winter conditions. And then when it comes in spring, depending on what the ice cover percentage is and what the flows are, it either lets the ice rot in place or it starts simulating ice jams. This is the first system of its kind in the country. There's a number of firsts in this. One, it runs all the time. Secondly, this ice cover information comes directly from radar set imagery that is processed by a company here called SECOR. So we partnered with them and the European Space Agency to create the world's first real-time river ice service. So satellites, radar satellites capture the ice coverage, and within 4 hours we have a processed product which goes into this model and which is used for it to predict whether it's going to be in a rotten place or is it going to be an ice jam condition. The whole system is incorporated on a web browser. It runs online. You just log into it, and it's got a dashboard system. So you have, for example, a summary of all the status. So it did, for example, say, did the water survey of Canada data come in? Yes. Did our data come in? Yes. Did the ice thickness data come in? Yes. So ice thickness, you're putting in real-time buoys, which are measuring the ice thickness. This is something we're partnering with a company out of Scotland and our local company, SECOR. It measures the ice thickness and sends the data every 6 hours. Then the numerical weather prediction data from Environment Canada, if that came in, then did HEC-HMS run? Did river ice run? Not only do we do all of this, it actually does a Monte Carlo on the river ice. So for example, the problem with ice jam prediction is that you don't know where the toe of the dam is going to form. So there's always a lot of uncertainty there. So what we actually do is we run 50 different simulations, and based on that, we come with 72-hour predictions with the 10 percentile, 50 percentile, and the 90 percentile. So it also does Monte Carlo. Now, Monte Carlo typically requires a lot more runs. We're trying to improve this. And this part, the Monte Carlo part, is based on work done by Dr. Carl Eric Lindensmith with the University of Saskatoon. So there's a number of publications now that we're writing on this. Here you get all of our current gauge readings. It tells you all the forecast data. So it tells you what the water percentile values are for ice. Sorry, our water level is 90 percentile value, the 50 percentile value, the 10 percentile value. We have this because we're using Monte Carlo. There's no water level here because this is for winter. In summer, what will happen is you won't see anything here, but you will see water levels here. And then we have the flows forecast for the next 3 days. And this is the forecast for the precipitation from the numerical weather prediction model for all the subwatersheds. This is the temperature prediction for the next 48 hours from numerical weather prediction model. And this is the ice coverage I told you from satellite imagery, remember? So we partner with the Canadian Space Agency and the European Space Agency, and we acquire this imagery. We get 3 to 4 images a week. It gets processed into open water, ice cover, and impacted ice. And it's automatically incorporated into the model. You can also zoom into specific locations, and at specific locations, you'll see what the flow is for the next 3 days. You will actually see what the current flow is and what the predicted 90 percentile, 50 percentile, and 10 percentile water levels are. You also get a profile for the whole river going from the dam all the way down to the lake. You can see the invert, the river invert here, and what are the predictions all along. And this way we know whether it's going to exceed the left bank or the right bank, and where will it do that. So this is really exciting. We've run this 2 years. This is our third year of running it now. It'll start, I mean, still running now, but the ice jam part starts from December, and we're really, really excited to be using this. So this is part of our multi-barrier action plan for public safety against floods, which is we have a flood forecasting system, we do monitoring, we have awareness, and that is by looking at adjacent rivers, and we have then local staff. So we don't rely on one thing, we rely on 4 things, because any one of these could be wrong, or things could, you could have errors there. We rely on a combination of 4 things, and the idea is to figure out, is the water level going to stay less than the riverbank? If yes, we continue monitoring and forecasting. If these 4 activities tell us the water level is expected to go above the bank level, we then bring our emergency measures organization into the rope, and they start informing people and take measures accordingly. So this is our multi-barrier action plan that we are trying to implement in all areas that we have flood forecasting systems. So going forward, I'm at the end, I'm sorry I raced through this. Going forward, the idea is to keep on doing these climate change floodplain mapping studies, because they give us the floodplain maps. They let us regulate development in these flood watersheds and the climate change watersheds. They also give us hydraulic infrastructure information, which can be used by the town and funding agencies. And we're using the triggers that come from there to improve the triggers in our hurricane season flood alert system. And as I mentioned, in 3 places where we are putting the weather forecast with the hydraulic model and the hydraulic models, we're stringing them together so that we can have real-time flood forecasting systems. So the one here in Churchill uses the hydrologic system to run in a web environment. The one for Humber also uses the hydrologic system, and the one for exploits is using HEC-RTS. And we're having a lot of trouble with HEC-RTS because it's we got the impression from the U.S. Army Corps of Engineers it was ready for real-time flood forecasting, but there are a number of complications in applying that to Canada. So we're trying to figure those out here as we go forward. Thank you. I rushed through a lot of stuff, but I wanted to give you a glimpse of all the different things we're doing.
Great. Thank you very much, Dr. Amir. Very interesting talk. Apparently, you're doing great work there. Lots of very comprehensive analysis of all the flood hazard issues in there. So everyone, if you have questions, you can use the chat window or just unmute yourself and ask your questions. I will start with the first question. So Dr. Khan, you mentioned that the area is very often affected by hurricanes. And to assess the impacts of climate change on either the precipitation or changes in the like storm surge, but specifically the precipitation. You mentioned that currently your Met Office, they use the downscale GCMs. Now the problem with that is that the GCMs cannot represent cannot simulate the hurricanes. They are at a very small scale. How do you factor in that uncertainty into your assessment?
So, Reza, you're talking about our climate change predictions or our hurricane season flood alert system? For the hurricane flood alert system, they actually run a hurricane model.
Okay.
So one of the models that AMEC does, they run an in-house hurricane model, right? You know that it has a higher resolution, it requires a lot more computing, but they do run that. So if they feel in a certain region, so typically we don't get hurricanes, we get post-tropical storms, right? We have had maybe 2 or 3 hurricanes that have hit us. But typically it's a post-tropical storm, but still for our hurricane season flood alert system, they use their in-house hurricane model for that. The Hurricane Wharf, that's what they use for that. Okay. With respect to our climate change predictions, that is a challenge there, but that is something that I don't look into. That's something that Joel Finnis looks at. Every time he does the update, he looks at, if you go in there, he'll tell you what the research issues are, and then he works on that. We never say that we have a complete handle on this, but we are presenting the best information. Yeah. And we don't use just downscale, he uses both downscaled and dynamic regression too, both. The ensemble consists of an equal mix of both. And it changes every time. So one of the challenges you find is Newfoundland is an island in the middle of an ocean, the island part. So when these GCM models work, they're moving from a water zone to a land zone. So you always have a lot of variability there. So if you look at the IPCC report, they show there's some parts of the world where the models don't agree. Newfoundland Labrador is one place because we're moving from an ocean environment to a coastal one. And for that reason, we defer to Dr. Joel Finnis, who goes through the models and selects what he thinks are the most representative of Newfoundland Labrador. He does that, and then he gets it peer reviewed by 2 or 3 organizations across Canada, right? It's not a perfect thing, but it's the best you can do. It's consistent, it follows the best science, and that's why we believe in updating that every 5 years. But if you have any more detailed questions that we can direct them to Dr. Joel Finnis. I think he'll be happy to answer.
Yeah, sure. Excellent. Thank you. There is a question from Farshad. Thanks, nice presentation. I'm just wondering if you are using storm surge data as well. If so,
yes,
we have these data available for the future. I think by future, he means climate change.
Right. We are using storm surge data for those watersheds that are impacted by storm surges. For example, the mapping that Dr. Reza is also working with some of our flood studies. So if you look at Stephen Crossing on the west coast, or if you look at Placentia here, so these places are impacted by storm surge. These are communities that are just on the coast. So for those, when you look at the study, there's also a return period on the storm surge. Currently, we have 2 issues. One, we don't have enough gauges. We like to have a lot more tide gauges and a lot more wind gauges, right? To try and figure that out better. The second problem we have is looking into the future. No, that we haven't incorporated that part yet. So in our climate change predictions, we don't look at the impact of climate change on storm surge. If somebody can suggest a methodology for doing that, we'll be glad to try it out. So when we do the studies, we suggest to the consultant what is the best you can, and then based on what they come back, we incorporate some of the stuff. But we're talking here in an academic environment, so I'm going to talk really frankly. One of the challenges is that when you're dealing with engineers, sometimes you find some engineers, depending on the training, are not that comfortable with climate change. A lot of the younger engineers, because of the training you get in school, are very comfortable with climate change. They understand the uncertainty. They realize there's a lot of uncertainty in the data, but they're comfortable working with that. But some of the older engineers, just because they've not been exposed to it, are not very comfortable with climate change, right? So this is something you will face in your career when you work. Depending on what somebody's training and exposure is, they might react differently to the uncertainty in climate change modeling, right? So that's why, for example, if you look at our climate change projections, we clearly show to you that the uncertainty in our climate change IDFs is in the same range as in the uncertainty that we see in our observed ones, right? The same range. So that gives you some reassurance that your values are not, way off. Sorry, I'm giving you an extended answer there, but does that answer your question?
Excellent, thank you. There's a question from Vinay. Are there other factors that can influence floodplain mapping, such as seismic activity?
Not in our area. We are in a very low seismic zone, so that's not a concern, and we don't incorporate that. That's not been a factor for us. One factor that does impact flood in the future is the land use in your flood watershed, the contributing watershed to your flood zone. So I didn't mention that one other thing we do in our studies is we now actually get a land cover analysis of the contributing flood watershed, and we use remote sensing for that. And we now use that every 10 years, we update that so we can see if there's any change in the flood watershed, contributing watershed, right? So we actually demarcate the contributing watershed there so we can control that. One thing that does change is the temperature. So I didn't go into this, but the climate change flood risk mapping that we have done for the lower Churchill River, we have also looked at the impact of temperature change when looking at the climate change scenario. And for example, because of temperature change, we find that the ice jams are going to be different because we won't have so much ice being generated, right? So that's something we're doing slowly, but that's been done in one study, not in other studies yet.
A question from Amir. Thank you for the presentation, Dr. Khan. Can you kindly explain how the stream level is being observed? And I'd like to know if the slightest change in stream level is being considered.
Okay,
I
stream
think
levels.
she's referring to the resolution maybe of your.
Yeah, for stream levels, our streams are monitored under a federal provincial program and by the Water Survey of Canada, which is part of Environment and Climate Change Canada, right? And yeah, so we don't do any flood forecasting systems for areas where we don't have a network. So for example, if I look at the Churchill River, I can't remember off the head, but we have at least 10, 15 stations there. All right, we have a lot of stations there. Humber River, again, at least 5 to 8 stations in there. Now, when you're looking at flood risk mapping, you don't go to sub centimeters. That resolution is not important because when you're doing your mapping, you don't have that resolution anyway, right? You have to look at the vertical resolution of your LiDAR. And if you look at that, then there's also the hydraulic model you're using. You're not looking, it's not that sensitive to that resolution at all. So and that's why another thing you have to realize when you've got stream stations, especially under ice conditions, you might have two next to each other, but they'll have different values because the ice in the river will impact the measurement. And so like one might read, let's say 97.1 meters, the other one might read 97.3 meters, okay? So you have to be aware of that variability there. So in some sites, we didn't go there, but in some sites like in Badger here, we actually have at critical points, we have two gauges. On the Churchill River, we have gauges on both sides of the river because we realize certain gauges can get plugged or there can be a localized dam in a place and those values can change. So to answer your question in brief, it's not that sensitive to your stream flow measurement accuracy. What Environment Canada does, I don't remember what the accuracy is, but it is more than enough for flood forecasting and flood warning.
I have a question related to a figure that you showed the differences between two DMs. One was the LiDAR and the other was.
Oh yeah, this one here.
Yeah.
That was something that was very shocking to her.
Yeah, could it be related because you showed a difference of like 30, 40 meters, right?
Yeah, it is huge. So when they came back, there some places it was showing a difference of 46 meters. Okay.
Would it be it's just a difference between DSM, DTM? Maybe one captures the buildings, the other just shows the bare earth.
I don't think so because the LiDAR was bare earth, right? And a lot of this area, this is a rural part of Newfoundland. This is Bay Roberts. It's a rural part. Again, I did not do this analysis. It was done by geomatics company C-Core here, remote sensing / geomatics company. And they came back and they illustrated to us that even for flat areas, there was a big variation in, again, it won't be everywhere, but this was a test case that we did. And the result was shocking enough for us to make sure that going forward, we only use LiDAR and we follow the federal standards on that now. So if you go to the federal standards, they've got federal LiDAR standards. And within that, they've got standards for flood risk mapping. They've got 3 levels of standards for highly urban areas, semi-urban areas, and rural areas. We go with highly urban area standard in our studies.
Thanks. Question from UDEC. Thank you, Dr. Khan. It was a very interesting presentation. I am wondering if you observe any improvement in cost of damage after the forecast system is implemented.
We haven't had because our flood forecasting systems are new, but we did a study once. We had Hurricane Igor that went here in 2010. And what we did is we looked at those communities that had flood risk mapping versus that they did not have flood risk mapping. And this was just a simple back of envelope analysis. And we found that roughly those communities that had flood risk mapping, the municipal infrastructure damage was less. This is just municipal infrastructure damage, okay? We're not looking at private property damage. So we had some numbers from, I'll go back a little bit here, please. Sorry. So these are damages that we have paid out under the disaster financial assistance arrangements. So we actually looked at those estimates and we looked at it for Hurricane Igor. And based on that, we got an idea that just for that one storm event, if a community had flood risk mapping, they were saving roughly $200,000 to $300,000, which is the cost of the study, essentially. So one flood event gave you back your investment study. But again, this was an extreme event, and this was just a back of envelope calculation. It was not a systematic calculation. One of the challenges is that all the damage estimates are not collected centrally. If you had the estimate centrally, you could do this kind of research, but the data is not always available.
These are the total damages, not the insurance claim.
Yeah, this is just the municipal damage, right?
Yeah.
And then there's also the other one, which is on the insurance. That's different, right? Now in Newfoundland, we did not have insurance for flooding until recently. So essentially, any damage that happened in the past, it was not covered by any other insurances, typically, unless for businesses.
Question from Muhammad Umi. Thank you for the amazing presentation. Do you think if we could have the same forecast model for low flows as well, does it go with somehow the same procedure?
For which place?
I think he's asking about low flows and whether predicting or forecasting the low flows is also as important as floods.
Low flows are important, but you don't use, at least I haven't seen any use of hydrologic models for low flows. Typically you use regional flood frequency analysis, right? You do a regional regression for low flows and you look at the 3-day, 7-day, 10-day low flows, right? So it's done a little differently. It is important. We also do that. If you go to our webpage, we have a low flow analysis for the whole of the province. And so when we have any development activities where somebody's going to use water, we use that to make sure they don't withdraw too much water. So it is important, but I've not seen any low flow forecasting systems. I haven't seen that. But if you do, please tell me. I'll learn something.
Yeah. There is a question from Chao, which I think you have already answered, but maybe if you want to add anything to that. Thanks for the presentation. I was wondering, do you have hurricane models for future? Also, have you considered the hurricane-induced rainfall in climate change? You already talked about that.
Yeah, we don't have the models for the flood alert system. HEC has their own hurricane WRF, and it's only for current conditions, not for future conditions.
And maybe I asked the final question. In modeling the urban areas, do you consider the drainage network or the sewer network, all these, and how they can play a role in flooding?
No, we don't. And the reason for that, that's a really good question. The reason for that is twofold. One is that under our mandate, under our act, storm drainage is not part of our jurisdiction. It's part of the municipal jurisdiction, right? And secondly, we are typically mapping along major river systems. So where the flooding is mainly from the river, right? It's not due to storm drainage incapacities or lack of capacity or lag time. When those situations do come up, we will only focus on riverine flooding, but we provide the data to the town so they can do more work. For example, here, when we're doing Churchill River, we also did the town of Happy Valley Goose Bay. So we also model the Churchill River. We also model all the streams inside the town. And for some of the streams where there wasn't much development, we were able to give them flood zones. But there were some areas where the streams had been modified by the town and there was extensive local drainage. For there, we were not able to do it. So what we did is we gave the data to the town and the town can do it because it's not part of a mandate. It's a mandate issue here.
Sure. Very interesting. Thank you very much, Dr. Han. Very interesting talk, very informative. I hope we can have you with us in future seminars. And
I'll be happy to do that. Thank you for this opportunity. Thank you.
Yeah, thank you. Thank you, everybody, for joining us. And we'll see you next week.
And please look at our webpage. All of it, this is on our webpage, okay?
Sure. Great. Thank you.